All right, in this video I want to do another example of using the second part of the fundamental theorem to do a very typical style problem on the AP exam. Before I do anything, let's just make up some plausible areas here to make our life easier. I think nothing will be lost if we do that. Let's just say this little sliver of area is 1. Let's say this area has, this section here is 4, and let's just say this is like 12. Okay, and this is again the function f. Okay, f, which is being referred to there. So this is the graph of a continuous function f with domain 0 to 10 is shown below. Let h of x equal the integral from 1 to x of f. All right, so the first thing we're asked is to find h of 1. So h of 1 is going to be the integral from 1 to 1 of f. But of course, that's just simply 0. Okay, so that one's straightforward. Is h of 0 positive or negative, I should say? Well, let's see. H of 0 is the integral from 1 to 0. Now I'm going to flip my limits of integration and put a negative just to make it easier for me to read. So this is the opposite of the integral from 0 to 1. The integral from 0 to 1 is negative 1, so this is negative, negative 1, which is 1. This question says, is h of 6 positive or negative? So our answer, of course, is positive. And this is h of 6 positive or negative? Well, h of 6 is the integral from 1 to 6. And so the integral from 1 to 6 is, let's see, so we're starting here at 1. And we're collecting that area of negative 4. And then we're collecting a little bit more, right? So like when we're summing area, we're getting that negative 4. And then we're getting that little piece up to 6. Now, I don't really know what the value of that is. Let's just call that a for now. So we're getting negative 4 plus a. And so I think that there's more negative area there than there is positive in that a region. So I would argue that this is less than 0. Now, for a justification on that, I think this is fine. If you really want to do something kind of elegant or impressive, you could say this is because... And what we're really trying to say is that the absolute value of the area from 1 to 5 is bigger than, right? So if I just put our function in absolute values, that'll collect all areas positive. That area is bigger than the integral from 5 to 6. So, and that's what we're calling a here, right? So this is what we're calling a. So I wouldn't get too hung up on that, but that's just a kind of a nice way of indicating that you know how to use some of the notation. But in any case, looks like we have a positive and negative. C says find the value of x for which h is a maximum. Okay, so now this is a question about h, not f, right? F has a maximum over there somewhere around 8 or whatever. This question is about h, which is collecting area under f. Now, to answer this, let's actually do both of these together, the max and the min. Let's make an f or an h prime number line over here. Okay, the domain of h is 0 to 10, right? 0 to 10, and we're making an h prime number line. Now, how do I find the derivative of h? Well, that's easy. It's the fundamental theorem. H prime is equal to f of x, right? That's the fundamental theorem of calculus, the second part. So what else would go on this number line? Well, our critical points. And our critical points are whenever h prime or f is equal to 0. And you don't have to do a lot of work for that. You just have to go know where to look. So in our graph, h prime, i.e. f, is 0, looks like at 1, and at 5, and at 9, but 9's an endpoint. So x equals 1 and 5. So those belong on our number line. And so what's happening on the in between there? So h prime, i.e. f, is negative before 1, and then negative between 1 and 5, and then it's positive. So I'm going to put negative, and then positive, which means my graph was decreasing, decreasing, and then increasing. So all of this is helpful because now I can get both of these questions, or at least make way on headway on both of these questions at once. The value of x for which h is a maximum. Well, by the first derivative test, looks like we have a max here at an endpoint, right? The derivative is positive, so the graph rises until 10. That creates a max. And if the graph starts decreasing, that also creates a max. So my endpoints there are maxes. I have no maxes in the interior, but I have a min where the derivative changes from negative to positive. So the min question is easy because that's the only candidate. Find the x value for which h of x is a minimum. That's at x equals 5. Find the x value for which h of x is a maximum. Well, in that case, there are two candidates, and we're just going to evaluate the function at both. So we're going to do h of 0 and h of 10. So h of 0 equals, and h of 10 equals. So h of 0, we already found, that was 1. And h of 10 would be, so it's the integral from 1 to 10. So what does that mean? We're going to collect that negative 4, and then we're going to add 12. So negative 4 plus 12, which is equal to 8. So the value of x for which h is a maximum is at x equals 10. Okay, when it says a maximum, it means like the maximum, the absolute maximum. Okay. E says, so the next two questions are about the second derivative questions, right? But they're the second derivative of h. So this says find the x-coordinates of all the inflection points of the graph of y equals h of x. Well, we need its second derivative, and we're just going to continue this relationship. H double prime would be the derivative of h prime, but that would mean that h double prime is f prime. So when we're analyzing the concavity of h, we're going to be looking at at the graph of f and looking for where it's rising and falling, right? F prime tells us about the direction of the curve. Okay, so let's analyze again for both these questions. Let's make a little h double prime number line. So 0 to 10. Okay, again, the second derivative tells us about concavity. Okay, so we want to know where h double prime, so let's see, the candidates for the inflection points. So that's going to be when h double prime or f prime is equal to 0. And so note, what we're going to look at the graph is different than what we did above. H double prime or f prime is 0 when we have horizontal tangents, right? Because this is the graph of f, and its derivative is 0 where we have horizontal tangents. So that's happening here at 1, at 4, and at, let's call this 8. Okay, let's call this value right below it. Let's assume that's 8. So those values, 1, 4, and, sorry, 1, I said that 4, but that's the area I made up. Let's call this 3.5. Okay, this value here is 3.5. That's the x value we'll use. 1, 3.5, and 8. Those are places where f prime, i.e. h double prime, is 0. So we're going to put those on our number line, okay? 1, 3.5, and 8. All right, and so now what do we look for? Well, we're looking for a change in the behavior of h double prime. In other words, a change in the behavior of f prime. So we're looking for where the graph above is changing from rising to falling or vice versa. So from 0 to 1, the graph is rising, right? F prime is positive because that graph's rising, so it's positive. Okay, which means that h double prime is concave up. And then it switches to decreasing until 3.5. So it's negative, means concave down. And then it switches to increasing, concave up, and then decreasing, concave down. Now again, remember, I know like the graph up here of f is increasing and decreasing. The reason I'm writing concave down is because we're really analyzing this, right? We're just getting that information from f prime. So an inflection point is wherever the second derivative changes sign, or the concavity changes, which will happen when the second derivative changes sign. So we have an inflection point here, we have one here, and we have one here. Okay, find the x-coordinates of all the inflection points, so that would be x equals 1, 3.5, and 8. Okay, and where's h concave up and concave down? Well, we have that info as well, right? So concave up would be on the interval 0 to 1, and then from 3.5 to 8, and that's it. And then concave down from 1 to 3.5, and then from 8 to 10. All right, so let's just kind of look at this at a glance here. So that was a good kind of overview of the types of questions that get asked on this concept. You're often given some graph, and then you're given an integral function in relation to that. And you have to know things like this in order to do your analysis properly. And again, if you look at the page here, I didn't really write the word area anywhere, right? So we're still using the basic principles we learned before. We're just applying them to this new idea of how to find the derivative of an integral function. All right, well, hopefully that helps you going forward.